Hello everyone and welcome back to another lesson. Have you ever wondered how ancient civilizations measured large distances without the technology we have today? Or how engineers ensure the structural integrity of massive bridges and skyscrapers? Well, today we're going to unlock the secrets behind these feats by exploring congruent triangles and how they help us measure distances and prove geometric statements. Our goal by the end of the lesson will be to use congruent triangles to prove statements and solve real-life problems. So let's dive right in. And you can see some examples of these man-made structures that we see, both ancient and modern, in these pictures here. Of course, we have the Golden Gate Bridge and the Eiffel Tower and the pyramids of Giza. It's helpful to review exactly what we mean by congruent triangles. Two triangles are congruent if all their corresponding sides and angles are equal. Essentially, they're exact copies of each other, even if one is a mirror image or rotated version of the other. So in this example, we have triangle ABC and triangle DEF, which are congruent to one another. And it's very important that we list the vertices in the same order that they correspond in. Vertex A corresponds with vertex D because angle A is congruent to angle D, and so on and so forth. We also have 5 different triangle congruence criteria that we can use to prove that triangles are congruent to each other. We have the side triangle congruence criterion. That says that if all 3 pairs of corresponding sides are equal, then the triangles are congruent. And as you can see, all 3 pairs of corresponding sides are marked as congruent in our little helpful diagram here. The side angle side criteria says that if 2 sides and the included angle of one triangle are equal to 2 sides and the included angle of another, then those 2 triangles have to be congruent. And it's important to understand that the included angle, what that means, included, is that the angle has to be between the 2 sides that we know are congruent, the 2 pairs of sides that we know are congruent to each other. The third criteria we have is the angle side angle criteria, and that says if 2 angles and the included side are equal in both triangles, then the triangles are congruent. This time the included side is the one between the angles. Then we have the angle side criterion, which says if 2 angles and a non-included side are equal, then the triangles are congruent. And finally, we have one special criteria that's only usable for right triangles, and that is the hypotenuse leg criteria, which says if the hypotenuse and one leg of a right triangle are equal to those of another, then those triangles have to be congruent. And we can use these different criteria to prove certain statements about triangles. So here we are given that we have a triangle ABC with side AB congruent to side BC. They have equal lengths. And our goal is to prove that angle A equals angle C. The angle A is congruent to angle C. What we are actually trying to prove here is we are trying to provide a proof of the base angles theorem for isosceles triangles that says that the base angles of isosceles triangles are also congruent. And I've added one more feature to this triangle that's going to let us do that. I've created a segment, DB, that is perpendicular to side AC and goes through point B at the top. That separates triangle ABC into 2 right triangles. So the way that we can prove the base angles theorem here is we can use one of our properties of congruence. We know that side DB is always going to be congruent to itself, and side DB occurs in both triangle ABD and triangle CBD. And we know that this segment, this side, is always going to be congruent to itself. And side DB happens to be the leg of one of the legs of each of those right triangles. So we have a leg of each right triangle that is congruent. And from our given information, we also know that the hypotenuse of each of those right triangles are congruent. So, using one of our triangle congruence criteria, by the HL, the hypotenuse leg criteria, triangle ABD is congruent to triangle CBD. Then it's just a simple matter of saying that since angle A corresponds to angle C, then angle A must be congruent to angle C because they are part of congruent triangles. And we can go ahead and mark that on our diagram. Angle A is congruent to angle C. That's what we set out to prove. We proved it using the hypotenuse leg criteria. We also have another task here. This task says to prove the following statement is true, that side AD is congruent to side CD. And again, we can use the hypotenuse leg theorem to say that triangle ABD is congruent to triangle CBD. Because again, we can use the reflexive property of congruence to say that side DB is always congruent to itself, side DB, which gives us a hypotenuse and a leg of each right triangle to show that the two triangles are congruent. And then we can say that since side AD corresponds to side CD, then since the triangles are congruent, we can say that side AD is congruent to side CD. Again, another example of the hypotenuse leg theorem. And we can mark that on our diagram as well. Of course, now we could also use the side congruence criteria to prove that the two smaller triangles are congruent. It also proves that if you have an isosceles triangle and you drop down a segment from the top of the isosceles triangle, the vertex angle, and it intersects the base at a right angle, then it always is a segment bisector of that base and an angle bisector of the vertex angle. Because if these two triangles are congruent, that also means that it splits that vertex angle in half exactly. We also have a couple of real-life applications. So, we can actually measure the width of a river without ever actually crossing the river using the power of congruent triangles. So you can use the following method to find the distance across a river without ever actually crossing the river or using an advanced piece of technology like a laser rangefinder or things like that. So we want to find the distance from point N to point P. Obviously, normally that would have us crossing the river. But what we can do is we can walk down the river and we can place a stake at point K on the side that we're on. Let's say we are on this side of the river. We can place a stake at point K on the near side so that the distance from K, the segment NK, is perpendicular to segment NP, so that this is a right angle. Then we want to find M, which is the midpoint of that segment we just created. We want to go back halfway to that point where we started, which was point N. That ensures that these two segments are congruent to each other. So finally, what we want to do is we're standing here at point M, halfway between point N and point K, and we can see point P on the other side of the river. That's where we want to go. So what you have to do is walk in a straight line, keeping on the line that goes between point B and point M. You want to walk, can follow that line until you come to point L. And point L is going to be on the line segment that is perpendicular to segment NA. So we form another right angle right here. So what we have here is we have an angle and a side, an angle and a side, but we can also use the vertical angles congruence theorem to say that this angle right here is congruent to this angle right here. So we can say the angle NMP is congruent to angle KML. So we have an angle, a side, and an angle, a side, and an angle. That lets us prove that triangle ENM is congruent to triangle LAM by the angle, side, angle congruence theorem. So now that we have proven that those two sides, that those two triangles rather, are congruent, we know, for instance, that side LK is going to be congruent to side NP. And you can use traditional methods. You can walk it out. You can use a tape measure, any pretty much standard method of measurement to find the distance between point L and point K on your side of the river. That's going to correspond to the distance across the river from point N to point P, allowing you to find the distance across the river without ever actually crossing the river. Very cool indeed. And finally, for our last example today, we can also use congruent triangles to prove that identical twins are the same height without actually measuring their height directly. And the way we could do that is if we use a tool called a clinometer. Let me write that word out for you. Clinometer. And if it helps, this root word, cline, sounds like incline. A clinometer measures angles. If you used a clinometer to measure the angle from the tops of the heads of these identical twins to a point exactly halfway between them. Right here. And that angle turned out to be the same, then we could prove that those two identical twins are the same height without ever actually measuring their height directly. As long as we knew that the distance between them, we don't even have to know the distance between them actually, we just have to know that the angle from the top of their head was measured to a point directly between them. And we would have an angle, and a side. An angle, and a side. So you could use the angle, side criterion to prove they are the same height. Now, in the real world, let's say, we are probably just going to use a tape measure or a yardstick, anything like that, a traditional method of measuring their heights and showing that they are the same height, but we don't have to. If we want to get creative with it, there are any number of ways that you can actually prove that two things are the same height using the power of triangles. And one thing I want you guys to notice, in a lot of our examples here, we are using right triangles specifically. And that's because there is a lot of power in right triangles that you'll learn about as you continue to do higher level math. There's actually a whole field of math that has to do with right triangles called trigonometry, which is the study of the relationships between the sides and the angles of right triangles and what we can discover using certain pieces of information. So, that is it for today. We explored how congruent triangles are not just abstract concepts, but powerful tools for solving real-world problems. From ancient surveyors measuring land to modern engineers designing structures, the principles of congruent triangles are essential. And remember that by establishing the congruence of triangles using criteria like side, 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 side angle side, hypotenuse leg, and others, we can prove geometric statements and calculate distances that are otherwise difficult to measure directly. So, thank you for your attention, and I encourage you to look for opportunities to apply these concepts in real life, and I'll see you in the next lesson. Thank you.